Hello, and welcome back to the second part of the introduction to fundamentals of daylight modelling. So let's see what's lying ahead of us with a peek at the module outline. There are 4 submodules following this introduction. The first one, titled Simulating Daylight, and that comprises 4 parts. First, we'll look at some of the real fundamentals of radiance and how it deals with different components of illumination, from arriving directly from the light source, indirectly from the source, as in from reflections or from the sky, because that's an extended source, and a little bit about specular reflections. We'll look at and see how we can create physically based skies. First, we'll look at sort of idealized cases and get some idea about how R-trace works. That's one of the main sort of programs for calculating illuminance at points. And then we'll see how we can use radiance to define skies of a known output. That means diffuse horizontal illuminance, say a 5,000 lux overcast sky. So see how that sky is created by radiance and how we would predict illumination under it. And then we'll complete submodule 2 with a look at predicting illuminance versus daylight factors under an overcast sky in a typical sort of shoebox office, looking along a line of points. And in submodule 3, we start to look in real detail at the ambient calculation and conclude with looking at how accurate radiance can be with one of the keystone validation studies that was carried out on radiance in the mid to late 90s. So the first part of the ambient calculation will look at the sampling rays. This is the hemispherical sampling technique which radiance uses to find extended light sources like the sky or reflected light in spaces. So we're going to be looking primarily at the ambient divisions parameter. And in the second part on the ambient calculation, we'll look at the ambient resolution, the ambient accuracy, and how the simulation progresses by using interpolation and the usefulness of carrying out an overture calculation. And the last part in submodule 3 is a look at the validation of radiance under real sky conditions using measured sky brightness patterns. So this was in a full-size space. So this was the most realistic representation of external conditions, I believe, to date of in a daylight simulation, and that allowed us to determine the absolute accuracy that is possible with radiance, and it showed to be extremely good indeed. Submodule 4, we'll look at climate-based daylight modelling. We'll look at the basics of daylight coefficients and how they can be implemented into a lighting simulation program. And then we'll see how that formulation was refined to come up with what's known as the 4-component method, which isn't a commonly used method. However, it allows you to see much more clearly how daylight coefficients work. So even though you'll probably end up using one of the multi-phase methods, seeing these lectures will give you good insights into the issues faced by using daylight curve efficiency radiance, and in particular why we ended up with the 5-phase method with the need to resolve these sort of specular transmission components. And we can conclude submodule 4 with an overview of a number of climate-based metrics that can be derived from a CBDM output of illuminance time series for the whole year. Okay, block 5.0 concludes with submodule 5, and we begin with some CBDM examples. So 2 examples, both from, well, 2004, 2005, both actually New York, the New York Times, daylighting evaluation, and then the daylight injury evaluation for Central Park Tower. So these were landmark studies that really pushed the envelope, showed what was possible with radiance, but also showed how these results could start to influence long-term planning and guideline recommendations for daylighting. And then that will finish off with a summary of where we got to, where next. But before all of that, submodule 2, simulating daylight, will be the next place to go for us. And look forward to seeing you then.